Yeah, what better way to finish off the fifth Australian Algebra Conference than Marcel Jackson? And he's going to be talking about some kernels of relations.
Thank you very much, John. Yeah, it's almost an honour, but the real reason I'm going last, of course, is because everybody knows I can't keep to time. And or it's possibly that I think I submitted an abstract a bit past the deadline. But anyway, the title isn't the greatest title because I haven't actually got a huge amount to say on kernels of relations, although it does perhaps tie in a little bit with what James was talking about earlier. And I guess I was a bit busy at this time of the year, so I thought this would be a nice little result to talk about. This year, well, actually it was a year or two ago now, really, but it appeared this year. I'd written a bit of a survey with a few bits and pieces with these two colleagues, Robin Hirsch and Ian Hodkinson, just about this general topic. And so I'm not going to give a survey on this topic, but I will sort of go over some aspects, including some nice, reasonably routine results once the appropriate machinery has been set up. And this is in collaboration with James East and Tim Stokes. Okay, so it's always good, even though it's the end, this maybe should be a warm down perhaps rather than a warm up, but everybody knows that groups are somehow the same, some sort of abstract version of permutations under composition, and that semigroups are somehow the same as transformations under composition, and in fact the same as partial transformations under composition, because we can compose partial transformations as we do in first year calculus when we compose a sine function with a log function, and suddenly the log is not defined on the non-positive numbers and so on. I mention this because sometimes people don't like the idea of composing partial functions, and yet in first year calculus, that's all we do virtually, and it always seems to be a bit perplexing to me. Anyway, and of course we can compose binary relations, and all three of these cases are associative, so they form semigroups. But because the obvious variant of the Cayley representation theorem works for semigroups in the first line here, and that's a sub-semigroup of the semigroup of all binary relations, because transformations are just particular kinds of binary relations, then all of these statements are equivalent. Except the first one's not true, and I've probably made this little trick before. The idea is to lull people into believing that this is obviously true, but in fact, Maltsev in 1939 looked at this and found that in fact this class does have an axiomatization, but it's a class of semigroups, of course. For example, the semigroup of natural numbers under addition is isomorphic to a semigroup of permutations because it's a sub-semigroup of the group of integers, but it doesn't mean it has inverse itself. And in fact, there's no finite axiomatization for the actual class of semigroups that are isomorphic to systems of permutations under composition, which is kind of neat, really. I mean, obviously they have to be cancellative, but there's infinitely many required laws. So of course, if we put inverse in there, everything's fine. And now we've got inverse, we could move on to inverse semigroups. And again, this relates a little bit to what James was speaking about. So inverse semigroups are in the same way the abstract class of partial injective maps under composition and inverse, because again, like in first year calculus, if we have an injective function, by which we mean an injective partial function, and it's injective, yes, injective, then it has an inverse. And maybe connecting slightly with the previous example, this is another well-known correspondence, which now no longer has any compositional structure, but it somehow has a similar flavor. On the right-hand side, we have some concrete objects that we're interested in. Yes, of course, when we study groups, we're often looking at groups of symmetry. So it's not just any permutations, they're permutations that preserve something. But nevertheless, ultimately, if we strip back the thing that's being preserved, we do have an algebra of permutations. So we are interested in the objects on the right, and we want to abstract, because we're algebraists and we plan to do mathematics, to some abstract object on the left, which now no longer talks about the things on the right specifically, but deals with the abstract algebra of these. So that's the game that we're looking at today. And since we've moved to binary relations here, and the title of the talk is Kernels of Relations, then perhaps it's interesting to think about how you might approach binary relations if you were trying to capture a full algebraic theory. So interestingly, logic in the 19th century, not that I'm claiming to be an expert, but was mostly based, or at least toward the end of the around 1900, was mostly based around the logic of relations. And this was through the work of De Morgan and Peirce and Schroeder here. You might know the Bernstein-Schroeder theorem, for example. And you might also know the Downward-Lowenheim-Skolem theorem in model theory, for example. And really, that's actually, Lowenheim was really proving this about systems of relations. And it was properties that can be witnessed on a family of relations, can be witnessed on a countable family of relations, or a family of relations over a countable set. So in the 1940s, Tarski tried to put this on an abstract algebraic footing, just like we have done with all of mathematics, effectively. And so the natural operations he thought of were composition, inverse, intersection, complement. Of course, if we have intersection and complement, we have union as well. I didn't write it here, but I think it's on the later pages. Just to keep this memorable, I'm using delta for the diagonal relation. So it's just the equals relation and the empty set. And because we've got complements, of course, we'd have the total relation. So he was able to show that every theorem that's proved up here could be proved in using a relatively small number of axioms, in fact, in this abstract language down here. Now, what are these objects? If we're trying to play this game of what are the abstract objects? Well, they're going to be some sort of monoid because composition is associative and we have an identity element. They're involuted because inverse of relations, where you just turn a relation around, is an involution. If I take the inverse of a composition, then it is just the reverse composition of the inverses. And it's, of course, a Boolean algebra because relations, binary relations, are just subsets of the square. And so intersection and union and complement are just a Boolean algebra of all subsets. But it turns out that it's a bit trickier than this. And there's actually a huge literature on these. Now, the fact that they're trickier is the main theme of this talk today. But the fact that something's tricky doesn't still make it quite useful, because the game we're playing today is sort of part of the general theory of these. And as we'll see in an example on the next page, individual cases are not subject to problems necessarily, and they can be really useful. So this is just a very quick example that comes from qualitative reasoning. So I've given a talk on qualitative reasoning before, but this is almost an independent discovery, or at least development, of some aspects of relation algebra by the computer science community. So these are supposed to be the 8 basic relationships between blobs in the plane. And we're not going to go into the detail of what blobs are. And this is just from the Wikipedia page, pretty much, for RCC8. So the relationships between blobs. So here in the top left here, we have X disjoint from Y. But in RCC8, we're allowed to talk about touching on the boundary. So this is externally touching. There's really 2 relationships here. X is inside Y. And the inverse of that would be that that X was over the top of Y, but this picture shows Y over the top of X. But you can see there's really there's a relationship and its inverse represented here, depending on whether you start with Y or start with X. Anyway, so you can go through and have a look at these. And strangely enough, these form a relation algebra in the sense of Tarski. So the basic relations here are dis, et, and so on, partially overlap down here. And composition of binary relations is just what they usually are. So here, the points in our representation as binary relations are going to be the blobs. So a point that we're acting on as a binary relation are the blobs, which here seem to be closed disks. And the composition of each of them defines a binary relation. They're clearly mutually exclusive, and their union is the total relation, because every pair of blobs is related by one of these, if they're closed disks, for example. And so it just turns out that when we compose things, we get an answer. But what I'm showing you here is just the atoms in this Boolean algebra. So they are the atomic relationships, but in general, we can combine them. So if I combine external touching with inside, well, here X externally touches Y, which is inside the green blob. And you can see that in this picture, X ended up overlapping the green blob, but it could have also been internally touching, and it could also be, X could have also had the relationship with the green blob of being properly inside. And they are the only possible relationships. And so we would say that the composition of those is the Boolean sum of the 3 basic relations here. So this is an example of a relation algebra that's used in, as I am told at least, by the geospatial reasoning people in just about every geospatial positioning system on the planet. So a little example very quickly, just because it is kind of neat. It's a little bit off topic. Here's a house. Let's just say it's properly within a property so the property of the house, and it borders a lake. And the lake contains an island, and there's a bridge connecting the island to the house. Now, I drew a picture here, and so if I asked you what the relationship between the bridge and the lake was, you'd go, well, it sort of properly overlaps. But a computer can't draw a picture, or it can, but it's not a useful way for it to reason usually. And also, when I drew this picture, maybe I drew a slightly misleading one so that that came out to be the answer. So you might have just followed my picture and gone, oh yeah, yeah, that's true. Is there a reason way we can deduce this? And there is, and it simply just involves working in this Boolean algebra that I mentioned, or this relation algebra from the previous slide. So based on the information, we had the bridge had this kind of property with the island. Now, because we didn't really specify that much about it. It connects the island, so it could overlap the island or it could just touch the edge. In this picture, it touched the edge, and so on. You can go through the information we have there. And the idea is you can compose these bits of information. So here was 2 pieces of information in the first line. And so I composed them because they were set up for composition. And I found that this was the answer. And I can go through like this. And I'm not going to go through this because we'll never get the talk done. But we end up finding that the relationship between the bridge and the lake is this condition, but also this condition. And so if it's related by both of them, it must be related by their intersection, because intersection is just like and. And when we intersect them, indeed, we find that it was just partial overlap. So this is the kind of context in which this is used. It's sort of like a reasoning system for information like this. So there's literally dozens and dozens, maybe, or you can make up as many as you want. So this talks more about the foundations of what these algebras look like, because these kinds of things are quite widely used, but there are a lot of quite technical mathematical properties that arise when you start to look at things like what is the complexity of that problem of deducing information that we just saw. So this connects with the sort of modern universal algebraic developments in constraint satisfaction problems, for example. So in the 1950s, Roger Linden showed that Tarski's axioms weren't complete. So there is a relation algebra that satisfies the obvious laws, but actually isn't isomorphic to an algebra of relations. And in 1964, Donald Monk used a neat projective plane construction to show that, in fact, there's no finite axiomatization. As we'll see in a moment, this turns out to be quite a common property in this area, but it does show that there's some challenges. But this is really the cherry. In fact, it's more like a whole cherry orchard on the cake, because this is a really, truly remarkable result. It's quite difficult to prove as well. The construction has an easy idea, but is extremely difficult to carry through to completion. So the idea is we're given a finite involuted Boolean monoid because we're hoping to have something isomorphic to a system of binary relations in this language. Is it actually isomorphic to a system of binary relations? That's an undecidable problem. And there's still some interesting natural variants of this that are unknown, such as the finite representation property, which is whether or not it's decidable given a finite algebra if it's isomorphic to a system of binary relations on a finite set. So more on that later. So Tarski's signature is one thing, but there are actually lots of operations, and perhaps if we weren't interested in all of them, we'd get by a little bit better. And very early on, Zaretsky showed that the obvious laws do axiomatize composition and relational containment. So you would be a semigroup, you would have an order, and the order should be preserved by composition. And that turns out to be necessary and sufficient. And something similar was shown by Bredekin and Shine here for composition and intersection. However, it's not true that finite algebras can be represented over finite sets. So there is some slight strange stuff starting to creep in. And then there's this one strange case of composition, set containment, inverse, and these 2 unary operations, domain and range, which were at least subliminally or peripherally alluded to in James's talk, but perhaps not in quite this context. So the domain is just the identity on the domain, and the range is just the identity on the range. And pretty much every other combination, so every other subset of task signature has no finite axiomatization. There are a few cases that are yet to be resolved, but they look complicated rather than easy. So bad behavior is pretty much the theme. And I've just put in brackets here, all I've done here is I've added on the diagonal relation. So if instead you're looking at ordered monoids, this is not finitely based. The same with semi-lattice ordered monoids. And if you drop the inverse and the set containment, then these are not finitely based. And in fact, that's true for a whole lot of variants of this. When it comes to undecidability, as mentioned before, that's a much more badly behaved property. And so slightly less is known perhaps, but Robin and I were able to show that if you restrict to this signature, which is sometimes called the Jornsen signature, then the undecidability proof of Hirsch and Hodgkinson continues to hold. Fortunately, you only need to use the easier part of that proof. And we also had a new construction, which is the main theme of today, for covering these signatures. So the first one is composition and set subtraction along with the identity. And then this is sort of like a dual case, and this is with complementation and set containment. And since this is in Western Australia, and Murray Neuseling, as he's currently known, was from UWA originally. This was something that Murray did in his thesis, was show that our argument didn't really require the identity. It does, but you can adapt it a bit to bypass it. So now we're on to kernels. And as mentioned, I don't have a huge amount to say, but except for the fact that the same bad behavior holds for kernels as well. So what is the kernel of a relation? It's just the kernel of a function, except that we're now dealing with a relation. So what is the kernel of a function? 2 points are related by the kernel of a function if they're mapped to the same point. So in this case, it's if they're related to the same point. And the co-kernel, which also came up in James' talk, is just the reverse. So here I have a binary relation R on 4 points. And I claim that the kernel, for example, relates 1 and 3 because 1 and 3 do map to the same point. Yeah, they both map to 2. And it relates 2 and 3 because 2 and 3 both map to 4. But they are the only things that are related here, other than the identity. So technically these are a reflexive relation, so they should have loops on all points, but I've dropped it. So one thing you can easily see is that this is a symmetric relation. So, and since it's also reflexive, so has loops everywhere, it's perhaps easier to drop the arrowheads and think of the kernel and the co-kernel as being just some sort of simple graph. So as mentioned, for functions, it's the usual equivalence relation, but for general binary relations, it isn't. Now, it's a neat little idea that, in fact, the computational problem of deciding, given a relation on a finite set, if it is actually the kernel of some other relation is NP complete. And I think I had a slide here, yes I did. And the reason is that a simple graph, so as mentioned, the kernel will be a symmetric relation, so let's just ignore the arrowheads, in which case it's just a graph. A simple graph on S is a kernel if and only if it can be covered by at most S many cliques. Because what happens here, if we look backwards from Z, there's going to be a whole clique of all things that map to Z. And so if there are only this many points, if there are only S many points, then there should be at most S many cliques, and it's easy to go the other direction. And the NP completeness comes because there is a quite closely related, well-known problem that's NP complete, which is, can you cover a graph by at most K many cliques? And so the trick is just to adapt that slightly so that you can make that K equal to the S, which is fairly routine. Okay, so here's the kernel and co-kernel again. And the little observation is that, and it follows immediately from this definition really up here, is that the kernel is just a relation composed with its converse. And I'm reading left to right as we would normally do for binary relations. And the co-kernel is just the opposite. And this is it was actually James who originally brought kernel and co-kernel to our attention, but it makes it sort of interesting in the context of this example I mentioned before. So in almost every signature that we know of, there is extremely bad behavior for understanding the abstract properties of binary relations. except for this one semi-complicated signature. And you can see that kernel and co-kernel is like a sub-signature of this, because you can express it using composition and inverse. So it's like a sub-reduct. And so the main result here is that, that it is in fact undecidable given a semigroup with two unary operations, ker and co-ker. Is it isomorphic to an algebra of binary relations? That's an undecidable problem again. So this is strange because it's the first case where we have a well-behaved signature like this one that has a sub-signature that becomes badly behaved again. So far, all the results have been that the bad behavior goes all the way to the top, or appears to at least. I'll just say representability here doesn't mean anything too technical. It just means, in this context of this talk, isomorphic to a system of binary relations. How am I going for time? Just about time to finish. Okay, so, but I do have some explanation. So you can extend this to some bigger signatures. So you can put on complement and diagonal and things like this. And you can also prove this abstract version that has nothing to do with binary relations at all. So if you're given a semigroup with two unary operations, K and C, is it a subreduct of an involuted semigroup where K is supposed to be this term function and K is supposed to be that, C is supposed to be this one. And just in preparing for this talk, I mentioned I was in some events today, and I've been quite busy actually. It was 9 till 4, this particular event. But it did give me an opportunity to use pen and paper because I wasn't allowed to work on my talk because there was too many people watching. And I have checked the details of this today, and it seems to be true that this is also undecidable for this signature, which was one I've been interested in for quite a long time. So what's the method? The method is based on encoding partial algebras. So this originally perhaps goes back to Trevor Evans, although the tricks for turning it into an algebra, as far as I'm aware, go back to someone called Stanislav Kublinovsky, probably in the early 90s. So Trevor Evans showed that the word problem, or the uniform word problem for a class, is decidable if and only if it's decidable which finite partial structures extend to a member of the class. So the uniform word problem so as an example, for example, if we don't have any requirement on our class K, if it's just the class of all binary, so groupoids here just means a set with a binary operation in this talk, sorry, then clearly we can determine if a finite example extends because you can complete it however you want if there's no restrictions. So it follows that the uniform word problem in the non-associative single binary operation is decidable. On the other hand, we know that the uniform word problem for groups is undecidable, so the partial group completion problem is undecidable. So that's our goal, is to encode this into this problem. So the trick is that you don't need to work with arbitrary partial groups. You can work with ones that whose Cayley table looks a bit like this. So there's some elements which I'm calling the square root of A, and every product between elements of the square root of A exist, but they could fall outside of the square root of A. But clearly there's only the square root of A squared many elements that can arise here. So it's still a finite table if the square root of A is finite. Now, there are some other conditions here which I'm not going to show you, but they're just some obvious ones. Maybe you should have inverses, for example. Amongst the elements that can be seen here, they're inverses. But otherwise, it's an incomplete table. And so what you can show is that, in fact, this problem is undecidable. Forget about the second line. That should be a finite group, but I can't be bothered. I don't have time. So input a square partial group. Does it embed into a group? Now, this has been mentioned, or at least the isotopy and autotopy ideas have been mentioned in the quasi-group talks because it makes sense. I won't go through this that much, but this is an isomorphic copy, or an example of the three-element group. And here I'm doing something really silly by switching the content of the table in those two columns. Now, this is a terrible thing to do when it comes to group theory, but it does still leave us with a Latin square table. And in fact, what we've managed to find here is just a quasi-group that's isotopic to the left, to the original group. So a homotopy is just the general notion of a homomorphism here, but instead of one thing, you have three of them, and they have to satisfy this sort of stretched homomorphism condition. And it turns out, and I won't go through it, that this exactly captures things like switching columns and switching rows, and it still preserves some sort of notion. So after a bit of work, you can actually show more than just what Evans showed, but you can combine some classic parts of quasi-group theory to show that it's also undecidable if a square partial group homotopy embeds into a group. And this is really useful, and just since this is the Australian Algebra Conference, and Heiko and Ian proved this interesting example which fits to this. So this is an example of a pattern that appears in an infinite group but no finite group, and there was a talk on this on a previous conference in this series. And you notice that it doesn't have any multiplication table, it doesn't have an axis or anything like that. It doesn't matter because it's actually up to homotopy embedding. So, so you can switch rows and columns without changing the labels. We don't care what the labels are. So let's see the trick. How are we going to turn a partial algebra into a total algebra? Here is a total group at the top. And what I'm doing is I'm making 3 copies of everything. So I've got the first copy, the second copy, and the third copy. And I've stretched it out so that now I'm only allowed products that start with the first copy times the second copy and fall into the third copy. Now, this was a total group, so it was already completely defined, but let's just say I had something stupid like this square partial group, which had some extra elements in it called C and D. Then there's nothing stopping me from still doing that down at the bottom here. Maybe I need to add on a few elements over here, but this is now a totally defined semigroup, and it's associative because all products of length 3 end up being 0. The only way to get a non-zero product was to take something from the first copy multiplied by the second copy, and the output lies in the third copy, so any further product is 0. So I've encoded this quite likely non-associative structure, that partial structure, as an associative total structure. So just quickly to finish off, because I must be getting to time, what does this look like for binary relations? So here is that group again, and I've represented in the conventional way one of the elements as a permutation on the set 0, 1, 2. So A here is a permutation. You can think of that when I did the stretching out and I made 3 copies. I'm going to now think about it as stretching out the number of points as well. So I'll make 3 lots of the points, 3 blobs. And my first copy will go between the left-hand blob and the middle blob. And my second copy of A will go between the middle and the right-hand one. And the third copy I haven't shown, but it would go between the left-hand one and the right-hand one. Now, the only thing to remember is these are just points. They're not ordered in any way. They're just points in a set. So this is a different picture of the same object. And you can see what's happened there is I've sort of moved it around. And that's the kind of thing that's corresponding to switching columns in the table without switching the names. And that's why we need the homotopy embedding idea to work properly for us, because when we come to looking at things represented in this way, we have no way to keep track of anything. They're just points that are sitting around. They're not in this nice configuration. So, and this corresponds to messing up the table. And so we need to be able to reconstitute it. So the idea of the proof is that you try and take that idea and put enough structure around it so that when you try and represent as binary relations in the appropriate signature, it forces those particular elements to be represented as injective partial functions, so that at least you have a picture a bit like this slightly messy, weird one that we had before, something like this. Then you also need enough structure around to make sure that you capture those blobs. So yes, they're points in the plane, but somehow you need to be able to talk about them so that you can at least say, well, the elements that have this property, the domain of those elements is we can put them here, and the domain of those elements, some other elements, are the ones we can put in the middle. The problem with this is that, of course, by adding in extra operations, then we have to generate lots of nasty things. So imagine what happens if we start to take unions of these and also complements. I don't even know how to draw that. It gets very nasty. So we have to come up with a way to capture what that could be in advance of knowing whether or not the thing actually corresponds to a picture like this in the first place. So the idea is, if it is embeddable, if the partial group does embed into a group, then we have a nice way to build representations pretty much based around the picture I just do here. Conversely, if we can represent isomorphically as an algebra of binary relations, then we can use the extra machinery to force it to be something like this. And that's pretty much the end of the talk. I did just have this one little thing because Vicky Gould and Mark Cambites quite a while ago proved that if you looked at the subreductive inverse semigroups corresponding to these two operations, then that also had undecidability. And I just thought I should note that that does correspond to a corresponding notion of kernel and co-kernel in the case of injective partial functions. I think that's probably time to finish.